Hello, my name is Gwendolyn Stripling, and I am the technical curriculum developer for machine learning here at Google Cloud. And welcome to Introduction to TensorFlow 2.0. TensorFlow is an end-to-end open source platform for machine learning. Introduction to TensorFlow is the third course of the machine learning on Google Cloud specialization. In the first course, you learned how Google does machine learning in terms of framing a business problem. In the second course, you launched into machine learning by learning about ML in practice, like how to perform exploratory data analysis, or how to deal with untidy data, or the mechanics of supervised learning, and about best practice model optimization techniques. In this course, our objectives are to help you understand the key components of TensorFlow, understand how to use the tf.data library to manipulate data in large data sets, show you how to create machine learning models in TensorFlow by using the Keras sequential and functional APIs for model creation with TensorFlow 2.0. You'll also learn how to train, deploy, and productionalize ML models at scale with Cloud AI Platform. So we will start our journey to TensorFlow 2.0 by first talking about core TensorFlow. And this is TensorFlow as a numeric programming library. Next, we'll look at datasets and feature columns and how to use them to design and build an input data pipeline. We'll look at how to classify structured data, for example, tabular data in a CSV file using feature columns. Feature columns serve as a bridge to map from columns in a file to features used to train a model. In a subsequent lab, we will use Keras to define the model. In Module 3, we show you how to build and train a deep neural network with TensorFlow 2.0 and the Keras sequential API. You'll learn how to use feature columns in a Keras model, and we'll show you how to save, load, and deploy a Keras model on Google Cloud AI Platform. Next, you'll train a neural network using the Keras functional API. In this module, we'll discuss embeddings and how to create them with the feature column API. We'll also discuss deep and wide models and when to use them. And we'll also help you understand how regularization can help improve the performance of a model. And then we'll summarize the concepts you've learned and discuss the next steps for working with TensorFlow 2.0. Let's get started.
In this module, we'll be going over some of the main concepts in TensorFlow 2. We'll be looking at tensors, variables, and the current API hierarchy. We'll then have a deep dive into the tf.data API and learn how to create input pipelines for models that train on data that's both in memory and also data that lives in multiple files. Lastly, we'll learn how feature columns are used to manipulate and prepare data so that it can be used to train neural network models. TensorFlow is an open source, high performance library for numerical computation, any numerical computation, not just for machine learning. In fact, people have used TensorFlow for all kinds of GPU computing. For example, did you know you could use TensorFlow to solve partial differential equations, which is super useful in physics fields like fluid dynamics? TensorFlow as a numeric programming library is appealing because you can write your computation code in a high-level language like Python and have it be executed in a very fast way at runtime. The way TensorFlow works is that you create a directed graph, or a DAG, to represent the computation that you want to do. In the schematic that you see here, the nodes, like those light green circles, represent mathematical operations, things like adding, subtracting, and multiplying. You'll see some more complex math functions like softmax and matrix multiplication, which are great for machine learning. Connecting all of those nodes together are the edges, which are the input and the output of those mathematical operations. The edges represent arrays of data flowing towards the output. Starting from the bottom are the arrays of raw input data. Sometimes we'll need to reshape your data before feeding it into the layers of a neural network, like the ReLU layer you see here. More on ReLU later. Once inside that ReLU layer, the weight is then multiplied across that array of data in a matmul, or matrix multiplication operation. Then a bias term is added, and the data flows through to the activation function. All right, I know what you're thinking. ReLU activation functions? Don't worry, let's start with the basics. I kept mentioning that array of data that's flowing around. What exactly does that mean? Well, that's actually where TensorFlow gets its name from. Starting on the far left, the simplest piece of data that you can have is called a scalar. That's a number like 3 or 5. It's what we call zero-dimensional, or rank 0. Now, we're not going to get very far passing around single numbers in our flow, so let's upgrade. Rank 1, where a one-dimensional array is called a vector. Now, in physics, a vector is something with magnitude and direction, but in computer science, you use the word vector to mean 1D arrays, like a series of numbers in a list. Let's keep going. A two-dimensional array is a matrix. A three-dimensional array? Well, we'll call it a 3D tensor. Scalar vector matrix, 3D tensor, 4D tensor, etc. So, a tensor is an n-dimensional array of data. So your data in TensorFlow are tensors. They flow through the graph, hence the name TensorFlow. So why does TensorFlow use directed graphs to represent computation? And the answer is portability. The directed graph is a language-independent representation of the code in your model. You can build a DAG in Python, store it in a saved model, restore it in a C++ program for low latency predictions. You can use the same Python code and execute it both on CPUs, GPUs, and TPUs. This provides language and hardware portability. In a lot of ways, this is similar to how Java Virtual Machine, or JVM, and its bytecode representation helps with the portability of Java code. As a developer, you write the code in a high-level language like Java, have it executed in different platforms by the JVM. Now, the JVM is itself very efficient and targeted to the exact OS and hardware written in C or C++. Similar deal with TensorFlow. As a developer, you write your code in a high-level language like Python and have it executed in different platforms by the TensorFlow execution engine. Now, the TensorFlow execution engine is very efficient and targeted toward the exact hardware chip and its capabilities, and it's written in C++. Portability between devices enables a lot of power and flexibility. For example, here's a common pattern. You train a TensorFlow model on the cloud, on lots and lots and lots of powerful hardware. Then you take the trained model and put it on a device out on the edge, perhaps a mobile phone or even an embedded chip. Then you can do predictions with the model right on the device itself, offline. Have you had a chance to use the Google Translate app on an Android phone? The app can work completely offline because the trained translation model is stored on the phone and is available for offline translation. Now I know what you're thinking. Due to the limitations of processing power on your phones, the edge model tends to be a bit smaller, which means they're generally less powerful than what's on the cloud. However, the fact that TensorFlow allows for models to run on the edge means a much faster response during predictions. So, TensorFlow is this portable, powerful, production-ready software to do numeric computing. It's particularly popular for machine learning. It's the #1 repository for machine learning on GitHub. Why is that? Well, it's popular among deep learning researchers because of the community around it and the ability to extend it to do some pretty cool new things. It's popular among machine learning engineers because of the ability to productionalize models, to do things at scale. The popularity among each of these groups increases the popularity in the other. Researchers want to see their methods being used widely, and implementing them in TensorFlow is a way of ensuring that. ML engineers want to future-proof their code so that they can use newer models as soon as they're invented, and TensorFlow can help them do that. Google open-sourced TensorFlow because it can empower many other companies, and because Google saw the potential of its massive community support. Let's take a look at the API hierarchy, which will consist of a spectrum of low-level APIs for hardware, all the way up to very abstract high-level APIs for super powerful tasks, like creating an 128-layer neural network with just a few lines of code written with the Keras API. Let's start at the bottom. The lowest layer of abstraction is the layer that's implemented to target the different hardware platforms. And unless your company makes hardware, it's unlikely that you'll do much at this level, but it does exist. The next level is the TensorFlow C++ API. This is how you can write a custom TensorFlow operation. You would implement the function that you want in C++, register it as a TensorFlow operation. You can find more details on the TensorFlow documentation on extending an op. I'll provide the link. TensorFlow will give you a Python wrapper that you can use just like you would use an existing function. Assuming you're not an ML researcher, you don't normally have to do this. But if you ever needed to implement your own custom op, you would do it in C++, and it's not too hard. TensorFlow is extensible in that way. Now, the core Python API is what contains much of the numeric processing code: add, subtract, divide, matrix multiply, etc. Creating variables, tensors, getting the right shape or dimension of your tensors and vectors, all of that is contained in the Python API. Then there are sets of Python modules that have high-level representation of useful neural network components. Let's say, for example, that you're interested in creating a new layer of hidden neurons within a ReLU activation function. You can do that just by using TF layers, just architect and construct it. If you want to compute the RMSE, or root mean squared error, as the data comes in, you can use tf.metrics. To compute cross entropy with logics, for example, which is a common loss metric in classification problems, you can use tf.losses. These modules provide components that are useful when building custom neural network models. Why are custom neural network models emphasized? Because you often don't need a custom neural network model. many times, you're quite happy to go with a relatively standard way of training, evaluating, and serving models. You don't need to customize the way you train. You're going to use one of the family of gradient descent-based optimizers, and you're going to backpropagate the weights and do this iteratively. In that case, don't write the low-level session loop. Just use an estimator or a high-level API, such as Keras. Speaking of which, the high-level APIs allow you to easily do distributed training, data preprocessing, the model definition, compilation, and overall training. It knows how to evaluate, how to create a checkpoint, how to save a model, how to set it up for TensorFlow serving, and more. And it comes with everything done in a sensible way that'll fit most of your ML models in production. Now, if you see example TensorFlow code on the internet that does not use the estimator API, ignore that code. Walk away. It's not worth it. You'll have to write a lot of code to do device placement, memory management, and distribution. Let the high-level API handle all of that for you. So, those are the TensorFlow levels of abstraction. On the side here, Cloud AI Platform is orthogonal, or it cuts across to this hierarchy. That means it goes from low-level to high-level APIs. Regardless of the abstraction level you're writing your TensorFlow code, using Cloud AI Platform, or CAIP, gives you that managed service. It's fully hosted TensorFlow. So you can run TensorFlow on the cloud, on a cluster of machines, without having to install any software or manage any servers. For the rest of this module, we'll be largely working with these top 3 APIs listed here. But before we start writing any API code and showing you the syntax for building machine learning models, we first really need to understand the pieces of data that we're working with. Much like in regular computer science classes, where you start with variables and their definitions before moving on to advanced topics like classes and methods and functions, that's exactly how we're going to start learning with TensorFlow components next. Now let's go over tensors and variables in TensorFlow. It's time to see some code. How can we bring life to each dimension of a tensor that we learned about earlier? And recall that a tensor is that n-dimensional array of data. When you create a tensor, you'll specify its shape. Occasionally, you'll not specify the shape completely. For example, the first element of the shape could be a variable, but that special case will be ignored for now. Understanding the shape of your data, or oftentimes the shape that it should be, is the first essential part of your machine learning flow. Here, for example, you're going to create a tf.constant 3. This is a zero-ranked tensor. It's just a number, 3, scalar. The shape, when you look at the tensor debug output, is simply an open parenthesis, close parenthesis. It's 0 rank. To better understand why there isn't a number in those parentheses, let's upgrade to the next level. If you passed in a bracketed list like 357 to tf.constant instead, you would now be the proud owner of a one-dimensional tensor, otherwise known as a vector. Now that you have that one-dimensional tensor, let's think about that. It'll grow horizontally, like things on the x-axis, by 3 units. Nothing on the y-axis yet, so we're still in one dimension. That's why the shape is 3, 2, 3, comma, nothing. All right, let's level up. Now we have a matrix of numbers, or a 2D array. Take a look at the shape, 2, 3. That means we have 2 rows and 3 columns of data. The first row being that original vector of 357, which also has 3 elements in length. That's where the 3 columns of data comes from. You can think of a matrix as essentially a stack of 1D tensors. The first tensor in the vector is 357. The second 1D tensor that's being stacked is the vector 468. Okay, so we've got height and we've got width. Let's get more complex. What does 3D look like? Well, it's a 2D tensor with another 2D tensor on top of it. Here you can see that we're stacking the 357 matrix on the 123 matrix. We started with 2 2x3 matrices, so our resulting shape of the 3D tensor is now 2, 2, 3. Of course, you could do the stacking in code itself instead of just counting parentheses. Take the example here. Our x1 variable is a TF constant constructed from a simple list, 2, 3, 4. That makes it a vector with a length of 3. x2 is constructed by stacking x1 on top of x1. That makes it a 2 by 3 matrix. x3 is constructed by stacking 4 x2s on top of each other. And since each x2 was a 2 by 3 matrix, that makes x3 a 3D tensor with a shape of 4.2.3. x4 is constructed by stacking x3 on top of x3. That makes it 2 4 by 2 by 3 tensors, or the final shape of a 4D tensor. Whew! If you've worked with arrays of data before, like NumPy, they're similar except for 2 points. tf.constant will produce tensors with constant values, whereas tf.variable produces tensors with variable values, or ones that can be modified. Now this will prove super useful later when we need to adjust those model weights during our training phase of our ML project. The weights can simply be a modifiable tensor array. Let's take a look at the syntax for each, as you'll become a ninja with combining, slicing, and reshaping tensors as you see fit. Here's a constant tensor produced by tf.constant, of course. Remember that 3, 5, 7 in a 1D vector? It's just stacked here to be that 2D matrix. Pop quiz. What's the shape of X? How many rows or stacks do you see? And then how many columns do you see? If you said 2 by 3 or 2 rows and 3 columns, awesome. When you're coding it, you can also invoke tf.shape, which is quite handy in debugging. Okay, much like you can stack tensors to get high level dimensions, you can also slice them down too. Let's look at the code for this for y. It's slicing X. Is it slicing rows, columns, or both? The syntax is let y be the result of taking X and take all rows, that's the colon, and just the first column. Keep in mind that Python is 0 index when it comes to arrays. What would the result be? Remember, we're going from 3D to 2D, so your answer should only be a single bracket list of numbers. If you said 5, 6, awesome. Again, take all rows, only the first index column. Don't worry, you'll get plenty of practice with this coming up in your lab. So we've seen stacking and slicing. Let's talk about reshaping with tf.reshape. Let's use the same 2D tensor, or matrix of values that is X. What's the shape again? Think rows and columns. If you said 2 by 3, awesome. Now, what if I reshaped X as 3 by 2, or 3 rows, 2 columns? What would happen? Well, essentially Python would read the input by row, and put numbers into the output tensor. It'll pick the first 2 values, put them in the first row. So you get 3 and 5. And the next 2 values, 7 and 4, into the second row. And the last 2 values, 6 and 8, into the third row. Again, 2 columns, 3 rows. That's what reshaping does. Well, that's it for constants. Not too bad, right? Next up are variable tensors. The variable constructor requires an initial value for the variable, which can be a tensor of any shape and type. This initial value defines the type and the shape of the variable. After construction, the type and shape of the variable are fixed. The value can be changed using one of the assign methods: assign, assign add, or assign sub. As we mentioned before, tf.variables are generally used for values that are modified during training, such as you might guess, the model weights. Just like any tensor, variables created with variable can be used as inputs to your operations. Additionally, all the operators are overloaded for the tensor class are carried over to variables. And TensorFlow has the ability to calculate the partial derivative of any function with respect to any variable. We know that, during training, weights are updated by using the partial derivative of the loss with respect to each individual weight. To differentiate automatically, TensorFlow needs to remember what operations happened in what order during that forward pass. Then during the backward pass, TensorFlow traverses this list of operations in reverse order to compute those gradients. Gradient tape is a context manager in which those partial differentiations are calculated. The functions have to be expressed within TensorFlow operations only. But since most basic operations like addition, multiplication, subtraction are overloaded by TensorFlow ops, these happen seamlessly. Let's say we want to compute a loss gradient. TensorFlow records all operations executed inside the context of tf.gradientTape onto a tape. Then it uses that tape and the gradients associated with each recorded operation to compute the gradients of a recorded computation using that reverse mode differentiation like we mentioned. There are cases where you may want to control exactly how gradients are calculated rather than using the default. These cases can be when the default calculations are numerically unstable, or you wish to cache an expensive computation from the forward pass, among other things. For such scenarios, you can use custom gradient functions to write a new operation or to modify the calculation of the differentiation.
In this lab, we look at tensors, which are multidimensional arrays with a uniform type. If you are familiar with NumPy, then tensors are kind of like NumPy arrays. All tensors are immutable, like Python numbers and strings, meaning you can never update the contents of a tensor, only create a new one. While tensors are immutable stateless objects, machine learning models must have changing state. As your model trains, the same code to compute predictions should behave differently over time. Variables are created and tracked via the tf.variable class. A tf.variable represents a tensor whose value can be changed by running ops on it. First, we define some basic and advanced tensor concepts. Then you perform single-axis and multi-axis indexing. And throughout the lab, you will learn how to create tensors and variables.
Hello and welcome. I'm Philip Meyer, a course developer with Google Cloud Platform, and this is a brief tutorial on using Quick Labs in this course. You're about to use the interactive hands-on labs platform called Quick Labs, which is part of Google Cloud. Quick Labs allows you to get practical hands-on experience with GCP and provisions you with Google Cloud credentials so you can access the GCP console at no cost. Once you reach the lab item in this course, click the Open button. You will then be prompted to provide the email that you want to use for your QuickLabs account. If you already have a QuickLabs account, you can use that email and then log in with your QuickLabs password. If you don't have a QuickLabs account, a new one will be created for you with the email that you provide. Once you're in QuickLabs, click the Start Lab button and wait until lab running is displayed. For each lab, you will have a timer with the remaining access time. You can see that right up here, and your lab will automatically end when the timer runs out. To get started, you want to click the Open Google Console button, and you're going to want to sign in with the username and password that are provided in this pane over here. So let me copy the username, click Open Google Console. I'm going to paste in that username. I'm going to go back and grab the password. I'm going to paste that in as well. And QuickLabs creates a new account for you each time you launch a lab. Therefore, you're going to have to click through some initial account setup windows. So in this case, I'm going to accept this over here. I don't need to do anything here. I can just click Done. And then once I'm in the GCP console, I can verify that I'm using the QuickLabs provided account and project. I first need to also agree to the terms of service. I click Agree and Continue. And then over here within the dashboard, I can see the project name, the project ID, the project number. I can also see the project ID up here. And I want to make sure that these are the same and that they match the connection details that we have in the QuickLabs page. So let me go and verify that this here corresponds to the project ID over here. And we can see it's just cut off slightly there. There we go. So indeed, we are using the right project. And we can also verify that we're using the right username. Click on this icon up here. We can see we're not logged in with our own account, but with the QuickLabs provided account. And this is very crucial. So let's also verify that this corresponds to the username that we are provided over here. Okay. Now, some labs track your work within the QuickLabs provided GCP projects. And if this is enabled, you'll see a score in the top right corner of the QuickLabs window, as you can see right here. And your score increases as each of these objectives here are met. And you can click on the score to view, as you can see here, the individual steps. So let me go ahead and complete these activities to show you what that looks like. Now that I have completed the lab, I can see that my score has been updated, and I'm ready to click End Lab. And once I click End Lab and confirm so, the QuickLabs provided project and any resources within that project will be deleted, and I can continue learning in Pluralsight. That's it for this tutorial. I'll show you what that looks like. Now that I have completed the lab, I can see that my score has been updated, and I'm ready to click End Lab. That's it for this tutorial. Remember to use the QuickLabs provided credentials to sign into the GCP console. Good
In this lab, you'll learn how the TensorFlow Python API works. You'll get to practice defining constants and variables, like the examples that you saw previously, and how to perform basic computations. You'll experiment with TF's automatic differentiation to implement a quick linear regression from scratch. All the IPython notebook code lives in our public repository, so you'll always have access to it. In the Quick Lab, you'll be provisioned a hosted Jupyter Lab notebook and Cloud AI platform, and you'll complete your work in the lab notebook. Keep in mind, you'll see the fully completed solution notebook as well, but try to do the entire lab without looking at the solution first. Good luck. In this lab, you'll learn how the
Hello, my name is Gwendolyn Stripling, and I am the Technical Curriculum Developer for Machine Learning here at Google Cloud. In this lesson, we look at how to design and build a TensorFlow input data pipeline. For those of you new to machine learning and data science, we begin with some introductory materials. So if you already know about TensorFlow data pipelines or have some experience constructing them, then skip this overview video and proceed to the next video. Just remember to do the labs and the quizzes. If you are new to machine learning, you will learn how to create datasets, how to load data using the tf.data API, how to construct feature columns, and how to train large datasets with the tf.data API. So let's start with a recap. In any ML project, After you define the business use case and establish the success criteria, the process of delivering an ML model to production involves the following steps. These steps can be completed manually or can be completed by an automated pipeline. For example, data extraction, data analysis, data preparation, model training, model evaluation, model validation, model serving, and model monitoring. We saw that there are two phases in machine learning, a training phase and an inference phase. And we learned that an ML problem can be thought of as being all about data. From a practical perspective, many machine learning models must represent the data or features as real numbered vectors because the feature values must be multiplied by the model weights. In some cases, the data is raw and must be transformed to feature vectors. Features, the columns of your data frame, are key in assisting machine learning models to learn. Better features result in faster training and more accurate predictions. As the diagram shows, feature columns are input into the model not as raw data, but as feature columns. Having efficient data pipelines is of paramount importance for any machine learning model because performing a training step involves 1. Opening a file if it has not been opened, 2. Fetching a data entry from the file, and 3. Using the data for training. Once you have completed steps 1 and 2, then how do you use the data for training? TensorFlow's dataset module, tf.data, is one way to help us build efficient data pipelines. And data pipelines are really just a series of data processing steps. The tf.data API enables you to build complex input pipelines from simple, reusable pieces. For example, the pipeline for an image model might aggregate data from files in a distributed file system, apply random perturbations to each image, and merge randomly selected images into a batch for training. The pipeline for a text model might involve extracting symbols from raw text data, converting them to embedding identifiers with the lookup table, and batching together sequences of different lengths. The tf.data API makes it possible to handle large amounts of data, read from different data formats, and perform complex transformations. We'll use the tf.data API quite a bit in this lesson. So there are multiple ways to feed TensorFlow models with data, and you will see those in the next videos. So let's get started.
When data used to train a model sits in memory, we can create an input pipeline by constructing a dataset using tf.data.dataset.fromTensors or tf.data.dataset.fromTensor slices. FromTensors combines the input and returns a dataset with a single element, while FromTensor slices creates a dataset with a separate element for each row of the input tensor. Here is an example where we'll use text line dataset to load in data from a CSV file. This is a dataset comprising of lines from one or more text files. The text line dataset instantiation expects a file name, and it has optional arguments, for example, like the type of compression of the files, or with this. When data used to train a model sits in memory, we can create an input pipeline by constructing a dataset using tf.data.dataset.fromTensors or tf.data.dataset.fromTensor slices. FromTensors combines the input and returns a dataset with a single element, while FromTensor slices creates a dataset with a separate element for each row of the input tensor. Here is an example where we'll use text line dataset to load in data from a CSV file. This is a dataset comprising of lines from one or more text files. The text line dataset instantiation expects a file name, and it has optional arguments, for example, like the type of compression of the files, text file, example, element, while FromTensor slices creates a dataset with a separate element for each row of the input tensor. Here is an example where we'll use text line dataset to load in data from a CSV file. This is a dataset comprising of lines from one or more text files. The text line dataset instantiation expects a file name, and it has optional arguments, for example, like the type of compression of the files or the number of parallel reads. The map function is responsible for parsing each row of the CSV file. It returns a dictionary from the file content. Once that's done, shuffling and batching and prefetching are steps that can be applied to the dataset to allow the data to be fed into the training loop iteratively. Please note that it's recommended that we only shuffle the training data. So, for the shuffle operation, you may want to add a condition before applying the operation to the dataset to ensure that it's training. Finally, we have to address our initial concern, loading a large dataset from a set of sharded files. An extra line of code will do. We'll first scan the disk and load a dataset of file names using the dataset.listFiles functions. It supports a glob-like syntax with stars to match file names with a comment pattern. It's pretty useful. Then we'll use a text line dataset to load the files and turn each file name into a dataset of text lines. We flat map all of them together into a single dataset. And then we map each line of text. We'll use that map to apply the CSV parsing algorithm and finally obtain a dataset of features and labels. You might wonder, why are there two functions for mapping, map and flat map? Well, one of them is to simply do a one-for-one transformation, and the other one is one-to-many transformations. Parsing a line of text is a one-to-one transformation, so we use map. When loading a file with text line dataset, one file name becomes a collection of text files. So that's a one-to-many transformation, and it's applied with flat map to flatten all the resulting text line datasets into a one. Dataset allows for data to be that each file to map. Well, when loading, flatten all the resulting text line datasets into a one. Dataset allows for data to be pre-fetched. Let's say that we have a cluster with a GPU on it. Without prefetching, the CPU will be preparing the first batch while the GPU is just hanging around doing nothing. Once that's done, the GPU can then run the computations on that batch. When it's finished, the CPU will start preparing the next batch and so forth. You can see that this is not very efficient. Prefetching allows for subsequent batches to be prepared as soon as their previous batches have been sent away for computation. By combining prefetching and multi-threaded loading and preprocessing, you can achieve a very good performance by making sure that each of your GPUs or CPUs are constantly busy. Now that you know how to use datasets to generate proper input functions for your models and to get them training on large out-of-memory datasets. But datasets offer a rich API for working on and transforming your data. So let's take advantage of it. As we think about modeling a real problem with machine learning, we first need to think about what input signals we can use to train that model. In this next section, let's use a common example. Why not real estate? Can you predict the price of a property? As you think about that problem, you must first choose your features, that is, the data that we'll be basing your predictions on. Why not try and build a model that predicts the price of an area of a house or an apartment? Your features could be the square footage, that's numeric, and the category. Is it a house or an apartment? So far, square footage, that's numeric. Numbers can be fed directly into a neural network for training, but we're going to come back to that later and how that's done. The type of the property, though, that's not numeric. This piece of information may be represented in a database by a string value, like house or apartment, and strings need to be transformed into numbers before being fed into a neural network. Remember, a feature column describes how the model should use raw input data from your features dictionary. In other words, a feature column provides methods for the input data to be properly transformed before sending it to a model for training. Again, the model just wants to work with numbers. That's the tensors part. Here's how you implement this in code. You use the feature column API to determine the features. First, a numeric column for square footage, then a categorical column for the property type. Two possible categories in this very simple model, house or apartment. You probably noticed that the categorical column is called categorical column with vocabulary list. Use this when your inputs are in a string or integer format, and you have an in-memory vocabulary mapping to each value to an integer ID. By default, out-of-vocabulary values are ignored. And as a quick side note, other variations of this are categorical column with a vocabulary file when inputs are in a string or integer format, but there's a vocabulary file that maps each value to an integer ID. A categorical column with identity, and that's used when inputs are integers in the range of 0 to the number of buckets, and you want to use the input value itself as the categorical ID. And finally, categorical column with a hash bucket. That's used when features are sparse in the string or integer format, and you want to distribute your inputs into a finite number of buckets by hashing them. In this example, after the raw input is modified by feature column transformations, you can then instantiate a linear regressor to train on these features. A regressor is a model that outputs a number. In our example, the predicted sale price of the property. That's a number. But why do you need feature columns in the context of model building? Do you remember how they get used? Let's break it down for this model type. A linear regressor is a model that works on a vector of data. It computes a weighted sum of all input data elements and can be trained to adjust the weights for your problem. Here we're predicting the sales price. But how can you pack your data into a single input vector that the linear regressor expects? Well, the answer is in various ways, depending upon what data that you're packing and in what area that your feature columns are using the APIs. That really comes in handy. It implements various standard ways, the API, of helping you pack that data into those vectorized elements. Let's look at a few. Here, values in your numeric column, they're just numbers. They can get copied as they are into a single element of the input vector. On the other hand, those categorical columns, they need to get one hot encoded. You have two categories, house or apartment. House will be 1, 0, and apartment will be 0, 1. A third category would be 0, 0, 1, and so on. Now the linear regressor knows how to take those features that you care about, pack them into an input vector, and apply whatever the linear regressor does. Besides the categorical ones that we've seen, there are many other mode feature column types to choose from. Columns for continuous values that you want to bucketize, word embedding, column crosses, and so on. The transformations they apply are clearly described in the TensorFlow documentation, so you always have an idea of what's going on. And we're going to take a look at quite a few of them here in code. A bucketized column helps with discretizing continuous feature values. In this example, if we were to consider the latitude and longitude, highly granular, right, of the house or apartment that we're training or predicting on, we wouldn't want to feed in the raw latitude and longitude values. Instead, we would create buckets that could group the ranges of values for latitude and longitude. It's kind of like zooming out if you're looking at just like a zip code. If you're thinking this sounds familiar, and just like building a vocabulary list for categorical columns, you're absolutely right. Categorical columns are represented in TensorFlow as sparse tensors. So categorical columns are an example of something that's sparse. TensorFlow can do math operations on sparse tensors without having to convert them into dense values first. And this saves memory and optimizes compute time. But as the number of categories of the feature grow large, it becomes infeasible to train a neural network using those one-hot encodings. Imagine that 0, 0, 0, 0, million zeros, 1. Recall that we can use an embedding column. Embeddings overcome this limitation. Instead of representing the data as a one-hot vector of many dimensions, an embedding column represents that data at a lower dimensional level, or a dense vector, in which each cell can contain any number, not just a 0 or a 1. We'll get back to our real estate example shortly, but first let's take a quick detour into the wild world of embeddings.
In this lab, you will learn how to load datasets from a source file, from a folder, or an application so that it can be processed for machine learning. To achieve that, you will learn how to load CSV files into a tf.data.dataset object, and you'll also see an example of loading data from NumPy arrays into a tf.data.dataset object. I hope you have fun. In this lab, you will learn how to load datasets from a source. In this lab, you will learn how to load datasets from a source file, from a folder, or an application so that it can be processed for machine learning. To achieve that, you will learn how to load CSV files into a tf.data.dataset object. In this lab, we will see a simple example of how to load an image dataset using tf.data. The dataset used in this example is distributed as directories of images, with one class of image per directory. We will first retrieve images using tf.keras.utils.get_file. We will then load images using Keras preprocessing, and also show you how to load images using tf.data.dataset objects. Finally, we will cover basic methods for training. Remember to take your time reading through and executing the code cells. You have more than one attempt to complete the lab, so don't worry if you run out of time on the first attempt. Good luck! In the upcoming lab, you classify structured data, such as tabular data in a CSV file, using feature columns. Feature columns serve as a bridge to map from columns in a CSV file to features used to train a model. We begin by learning how to load a .csv file using pandas. Then we learn how to create an input pipeline using tf.data. And finally, you see how to create multiple types of feature columns. Good luck! This lab focuses on tf.record and tf.example. In this lab, you will create, parse, and use tf.example messages. You will also serialize, write, and read tf.example messages to and from .tf.record files. To read data efficiently, it can be helpful to serialize your data and store it in a set of files that can be read linearly, each one having 100 to 200 megabytes in size. This is especially true if the data is being streamed over a network. This can also be useful for caching any data preprocessing that you will do. At the end of this lab, you will have learned how to use the tf.record format for storing data, how to use the tf.example message type, and also how to read and write a tf.record file. Practice with the lab yourself by reading through the notebook comments and executing the code cells. You're encouraged to edit the code to ensure you understand what each part does. Good luck!
Data is one of the most crucial components of your machine learning model. Collecting the right data is not enough. You also need to make sure that you put in the right processes in place to clean, analyze, and transform the data as needed so that the model can take the most signal from that data as possible. And models which are deployed in production especially require lots and lots of data. This is data that likely won't fit in memory and can possibly be spread across multiple files or may come from an input pipeline. The tf.data API enables you to build those complex input pipelines from simple reusable pieces. For example, the pipeline might be a structured dataset that requires normalization, feature crosses, or bucketization. An image model might aggregate data from files in a distributed file system, apply random skewness to each image, and merge randomly selected images into a batch for training. The pipeline for a text model might involve extracting symbols from raw text data, converting them to embedding identifiers with a lookup table, and then batching together sequences of different lengths. The tf.data API makes it possible to handle large amounts of data, read it in different file and data formats, and perform those complex transformations. The tf.data API introduces the tf.data.dataset abstraction that represents a sequence of elements, in which each element consists of one or more components. For example, in an image pipeline, an element might be a single training example with a pair of tensor components representing the image and its label. There are two distinct ways to create a dataset. A data source constructs a dataset from data stored in memory or in one or more files. Or a data transformation constructs a dataset from one or more tf.dataset objects. Large datasets tend to be sharded or broken apart into multiple files which can be loaded progressively. Remember that you train on mini batches of data. You don't need to have the entire dataset in memory. One mini batch is all you need for one training step. The dataset API will help you create input functions for your model that load data in progressively, throttling it. There are specialized dataset classes that can read data from text files like CSVs, TensorFlow records, or fixed-length record files. Datasets can be created from many different file formats. Use text-line dataset to instantiate a dataset object, which is comprised of, as you might guess, one or more text files. TF record dataset, TF record files. Fixed-length record dataset is a dataset object from fixed-length records or one or more binary files. For anything else, you can use the generic dataset class and add your own decoding code. Okay, let's walk through an example of TF record dataset. At the beginning, the TF record op is created and executed. It produces a variant tensor representing a dataset which is stored in the corresponding Python object. Next, the shuffle op is executed, using the output of the TF record op and its input, connecting the two stages of our input pipeline so far. Next, the user-defined function is traced and passed as attributes to the map operation, along with the shuffle dataset variant input. Finally, the batch op is created and executed, creating the final stage of our input pipeline. When the for loop mechanism is used for enumerating the elements of the dataset, the iterable method is invoked on the dataset, which triggers the creation and execution of two ops. First, an anonymous iterator loop is created and executed, which results in the creation of an iterator resource. Subsequently, this resource, along with the batch dataset variant, is passed into the makeIterator op, initializing the state of the iterator resource with the dataset. When the next method is called, it triggers creation and execution of the iterator getNext op, passing in the iterator resource as the input. Note that the iterator op is created only once, but executed as many times as there are elements in the input pipeline. Finally, when the Python iterator object goes out of scope, the delete iterator op is executed to make sure that the iterator resource is properly disposed of. Or to state the obvious, properly disposing of the iterator resource is essential, as it is not uncommon for your iterator resources to allocate, say, hundreds of megabytes to gigabytes of memory because of internal buffering. In this lab, you'll learn how to train on large datasets that aren't going to fit in memory. TensorFlow has that API called datasets that can handle this and feed your model while loading the data progressively from disk. Practice with the lab yourself by reading through the notebook comments and executing the code cells. Edit the code to ensure that you understand what each part does, and then come back and watch the wrap-up video. We'll give you a complete walkthrough. Note that you have more than one attempt to try this lab, so don't worry if you run out of time on your first attempt. Good luck.
In this lab, you will be using two tools which are part of the Fairness Indicators suite of tools: TensorFlow Data Validation or TFDV, and facets. TensorFlow data validation is one tool you can use to analyze your data to find potential problems in it, such as missing values and data imbalances. Sometimes these imbalances can lead to fairness disparities. The TFDV tool analyzes training and serving data to compute descriptive statistics, infer a schema, and detect data anomalies. Facets is a tool that provides a succinct visualization of these statistics for easy browsing. In this lab, we will use TFDV to compute descriptive statistics that provide a quick overview of the data in terms of the features that are present and the shapes of their value distributions. Then we use facets to visualize these statistics using the several comments dataset. First, we will show you how to use TF records to load record-oriented binary format data. Then, you will learn how to use TensorFlow data validation to generate statistics and facets to visualize the data. A practical use case is to learn how to use the TFDV widget to answer questions. And finally, you will learn how to analyze label distribution for subset groups.
In this module, we'll talk about activation functions and how they're needed to allow deep neural networks to capture non-linearities of your data. Then we'll learn how the sequential and the functional APIs of Keras allow us to simply write neural network models, and then how we can deploy those models to Cloud AI Platform to serve them in a scaled fashion. Lastly, we'll discuss one of my favorite topics, which is how you can avoid overfitting your models by applying regularization techniques during model training. So let's jump right into it. Next, let's take a look at activation functions and how they help training deep neural network models. Here's a good example. This is a graphical representation of a linear model. We have three inputs on the bottom, x1, x2, and x3, shown by those blue circles. They're combined with some weight, w, given to them on each of those edges. Those are the arrows that are pointing up. And that produces an output, which is the green circle there at the top. There's often an extra bias term that's added in, but for simplicity that isn't going to be shown here. This is a linear model, since it's of the form y equals w1 times x1 plus w2 times x2 plus w3 times x3. Now, we can substitute each group of weights for a similar new weight. Does this look familiar? It's exactly the same linear model as before, despite adding a hidden layer of neurons. How is that so? What happens? Well, the first neuron of the hidden layer that's on the left takes the weights from all the three input nodes. Those are all the red arrows that you see here. And you can see that's little w1, little w4, and little w7, all combining respectively, as you see clearly highlighted. Now, as you take the new weight, and that's the output of the first neuron, which in our case is little w10 now, as one of those three weights going into the final output. You'll see that we do this 2 more times for the other 2 yellow neurons and their inputs, respectively from x1, x2, and x3. And you can see that there's a ton of matrix multiple yellow neurons and their input in the scenes. Honestly, in my experience, machine learning is basically taking arrays of various dimensionality, like 1D, 2D, or 3D, and then smashing them and multiplying them against each other, where one array or a tensor could be a randomized array of starting weights of the model, and the other is the input dataset, and yet a third is the output array or tensor of the hidden layer. You'll see behind the scenes, it's honestly just a lot of simple math, depending upon your algorithm, but a lot of it is done really, really, really quickly. That's the power of machine learning. Here, though, we still have a linear model. How can we change that? Let's go deeper. I know what you're thinking. What if we just add another hidden layer? Does that make it a deep neural network? Well, unfortunately, this once again collapses all the way back down into a single weight matrix multiplied by each of those three inputs. It's the same linear model. We can continue this process of adding more and more and more hidden neuron layers, but it would be the same result, albeit it would be a lot more costly computationally for training and for predicting, because it's a much more complicated architecture than we actually need. So here's an interesting question. How do you escape from having just a linear model? Well, by adding nonlinearity, of course. That's the key. The solution is adding a nonlinear transformation layer, which is facilitated by a nonlinear activation function, such as a sigmoid, tanh, or ReLU. In thinking of the terms of the graph that's created by TensorFlow, you can imagine each neuron actually having two nodes. The first node being the result of the weighted sum, w times x plus b, and the second node is the result of that being passed through the activation function. In other words, there are the inputs to the activation function followed by the outputs of the activation function, so the activation function acts as a transition point between layers. That's how you get that nonlinearity. Adding in this nonlinear transformation is the only way to stop the neural network from condensing back down into a shallow network. Even if you have a layer with nonlinear activation functions in your network, if elsewhere in your network you have two or more layers with linear activation functions, those can all still be collapsed down into just one network. So usually, neural networks have all layers nonlinear for the first n-1 layers, and then have the final layer transformation be linear for regression, or sigmoid or softmax for classification. It all depends on what you want that final output to be. Now, you might be thinking, what nonlinear activation function do I use? There's many of them, right? You got sigmoid, you got scaled and shifted sigmoid, you have the tanh, or the hyperbolic tangent being some of those earliest. However, as we're going to talk about, these can have a saturation, which leads to what we call the vanishing gradient problem, where with zero gradients, the model's weights don't update. Anything times zero, right? And training halts. So the rectified linear unit, or ReLU for short, is one of our favorites because it's simple and it works really well. Let's talk about it a bit. In the positive domain, it's linear, as you see here, so we don't have that saturation, whereas in the negative domain, the function is 0. Networks with ReLU hidden activations often have 10 times the speed of training than networks with sigmoid hidden activations. However, due to the negative domain's function always being 0, we can end up with ReLU layers dying. Now, what I mean by that is you'll start getting inputs in the negative domain, and then the output of the activation will be 0, negative times 0, 0, which doesn't help in the next layer getting the inputs back into the positive domain. Still going to be 0. This compounds and creates a lot of 0 activations. During backpropagation, when updating the weights, since we have to multiply our error's derivative by the activation, we end up with a gradient of 0, thus a weight update of 0. Thus, as you can imagine with a lot of zeros, the weights aren't going to change and the training fails for that layer. Fortunately, this problem's been encountered a lot in the past, and there's a lot of really cool, clever methods that have developed to slightly modify the ReLU to avoid the dying ReLU effect and ensure training doesn't stall. But still with much of the benefits that you would get from normal ReLU. So here's the normal ReLU again. The maximum operator can also be represented by a piecewise linear equation where less than 0, the function 0, and greater than 0, the function is x. Some extensions to ReLU meant to relax the nonlinear output of the function and to allow small negative values. Let's take a look at some of those. Soft plus, or a smooth ReLU function. This function has its derivative as the logistic function. The logistic sigmoid function is a smooth approximation of the derivative of the rectifier. Here's another one. The leaky ReLU function, I love that name, is modified to allow those small negative values when the input is less than 0. Its rectifier allows for a small non-zero gradient when the unit is saturated and not active. The parametric ReLU learns parameters that control the leakiness and shape of the function. It adaptively learns the parameters of the rectifiers. Here's another good one. The exponential linear unit, or ELU, or ELU, is a generalization of the ReLU that uses a parameterized exponential function to transform from positive to small negative values. Its negative values push the mean parameters. The parametric ReLU learns parameters that control the leakiness and shape of the function. It adaptively learns the parameters ReLU output of the function and to allow small negative values. Let's take a look at some of those. Soft plus, or a smooth ReLU function. This function has its derivative as the logistic function. The logistic sigmoid function is a smooth approximation of the derivative of the rectifier. Here's another one. The leaker allows that control the exponential linear negative values. Its negative values push the mean of the activations closer to 0. That means that activations are closer to 0 enable faster learning as they bring the gradient closer to a natural gradient. Here's another good one. The Gaussian error linear unit, or GLU, that's another high-performing neural network activation function, like the ReLU, but its nonlinearity results in the expected transformation of a stochastic regularizer, which randomly applies the identity or zero map to that neuron's input. I know what you're thinking. That's a lot of different activation functions. I'm very much a visual person. Here's the quick overlay of a lot of those on that same XY plane. Next, let's talk a little bit about backpropagation. In one of those traditional courses for machine learning or neural networks, you'll hear a lot talked about backpropagation at a very granular level. But at some point, it's kind of like teaching people how to build a computer code compiler. Yes, it's essential for a super deep understanding, but not necessarily needed for an initial understanding. The main thing to know is that there is an efficient algorithm for calculating those derivatives, and TensorFlow will do it for you automatically. Now, there are some really interesting failure cases that you should know and that we're going to talk about, such as number 1, vanishing gradients, number 2, exploding gradients, and number 3, those dead layers. First, during the training process, especially for deep neural networks, gradients can vanish. Each additional layer in your network can successfully reduce signal versus the noise. Not good. An example of this is using the sigmoid or tanh activation functions throughout your hidden layers. As you begin to saturate, you end up in the asymptotic regions of the functions, which begin to plateau. That slope is getting closer and closer and closer to approximately 0. When you go backwards through the network during backprop, your gradient becomes smaller and smaller and smaller. And because you're compounding all these small gradients until the gradient completely vanishes. When this happens, your weights no longer update, and therefore training will grind to a halt. A simple way to fix this is to use non-saturating, non-linear activation functions such as your relose or your elose that we just talked about. So, if they're to fix this, is to use non-saturating, non-linear activation functions such as your relose or your elose that we just talked about. So, if they're not vanishing, what's the opposite end of the spectrum? Number 2, you can have exploding gradients. By this we mean they get bigger and bigger and bigger until your weights get so large that you overflow during training. Even when starting with relatively small gradients, such as a value of 2, it can compound and become quite large over many successive layers. This is especially true for sequence models with long sequence lengths. Learning rates can be a factor here because in our weight updates, remember that we multiply the gradient with the learning rate and then subtract that from the current weight. So even if the gradient itself isn't that big, with a learning rate greater than 1, then it can actually become too big and cause problems for us in our network during training. There are many different techniques to try and minimize this, such as weight regularization and smaller batch sizes. Another technique is gradient clipping, where we'll check to see if the norm of the gradient exceeds some certain threshold that you set. It's a hyperparameter that you can tune ahead of training. And if so, you can rescale your gradient all the way down to your preset maximum. Another useful technique that you'll hear talked about a lot is batch normalization, which solves a problem called internal covariate shift. It speeds up training because gradients will then flow better. You can also use a higher learning rate, and you might be able to get rid of dropout, which slows computation down due to its own kind of regularization due to mini batch noise. So how do you do it? Well, to perform batch normalization, you first find the mini batch mean, then the mini batch's standard deviation, then you normalize the inputs to that node, then scale and shift by y equals gamma times x plus beta, where gamma and beta are learned parameters. If gamma is the square root of x and beta is the mean of x, the original activation is restored. This way you can control the range of your inputs so that they don't unnecessarily become too large. Ideally, you would like to keep your gradients as close to 1 as possible, especially for very deep neural networks, so you don't compound and eventually overflow or underflow. All right, last up. That third common failure of gradient descent is that your ReLU layers can die. Fortunately, using TensorBoard, we can monitor the summaries during and after training of our deep neural network models. If you're using a pre-canned or pre-created deep neural network estimator, there's automatically a scalar summary saved for each DNN hidden layer showing the fraction of 0 values of the activations for that layer. The more 0 activations you have, the bigger the problem you have. ReLUs will stop working when their inputs keep giving them in the negative domain, which results in an activation value of 0. It doesn't end there because their contribution to the next layer is 0, but despite that the weights connecting it to the next neurons, their activations are 0, thus the input becomes 0. Now, a bunch of zeros coming to the next neuron doesn't help it get into the positive domain. And because these neurons' activations also become 0, you can see that that problem continues to cascade like we talked about. Then you perform backprop and the gradients are 0, and then training doesn't update during the weights, so it's not good. We talked about using those leaky or parametric ReLUs, or even the slower ELUs, but you can also lower your learning rates to help stop ReLU layers from not activating and thus dying. A large gradient, possibly due to too high of a learning rate, can update the weights in such a way that no data point will ever activate it again. And since the gradient is 0, we won't update the weight to something more reasonable, so the problem persists indefinitely. Let's see how TensorFlow 2 and Keras make it easy to write those models to build pretty cool neural networks. TF.Keras, again, that's TensorFlow's high-level API for building and training your deep learning models. It's also really useful for fast prototyping, state-of-the-art research, and productionalizing these models. And it has a couple key advantages that you should be familiar with. It's user-friendly. Keras has a simple, consistent interface optimized for your common ML use cases. It provides clear and actionable feedback for user errors, which makes it kind of fun to write ML with. Its modular and composable Keras models are made together by connecting configurable building blocks together with just a few restrictions. Also, it's really easy to extend and write your own custom building blocks to express new ideas on the leading edge of machine learning research. You can create new layers, create new metrics, loss functions, and develop your whole new state-of-the-art machine learning model should you wish. Here's an example. A sequential model, like you see here in code, is appropriate for a plain stack of layers, where each layer has exactly one input tensor and one output tensor. Sequential models are not really advisable if the model that you're building has multiple inputs or multiple outputs, any of the layers in the model have multiple inputs or multiple outputs, the model needs to do layer sharing, or the model has a nonlinear topology, such as a residual connection, or if it multi-branches. Let's look at some more code. In this example, you'll see that there's one single dense layer being defined. That layer has 10 nodes, or neurons, and the activation is a softmax. And the activation being softmax tells us we're probably doing classification. With a single layer, the model is linear. This example is able to perform logistic regression and classify examples across 10 classes. With the addition of another dense layer, the model now becomes a neural network with one hidden layer. But it's possible to map nonlinearities through that ReLU activation we talked about before. Once more, you're going to add one layer, add to the network. Now it's becoming a deeper neural network. Each additional layer makes it deeper and deeper and deeper. Now, let's try that again. Here's another deeper neural network architecture. Needless to say, the deeper a neural net gets, generally the more powerful it becomes in learning patterns from your data. But one thing you really have to watch out for is this can cause the model to overfit, as it may almost learn all of the patterns in the data by memorizing it and not generalize to unseen data. Now, there are mechanisms to avoid that, like regularization, and we'll talk about those later. Once we define the model object, we compile it. During model compilation, a set of additional parameters are passed to the method. These parameters will determine the optimizer that should be used, the loss function, and the evaluation metrics. Other parameter options could be the loss weight, the sample weight mode, and the weighted metrics if you get really advanced into this. What is a loss function? Well, that's your guide to the terrain, telling the optimizer when it's moving in the right or wrong direction for reducing the loss. Optimizers tie together that loss function and the model parameters by actually doing the updating of the model in response to the output of the loss function. In plain terms, optimizers shape and mold your model into its most accurate possible form by playing around with those weights. An optimizer that's generally used in machine learning is SGD, or stochastic gradient descent. SGD is an algorithm that descends the slope, hence the name, to reach the lowest point on that loss surface. A useful way to think of this is think of that surface as a graphical representation of the data, and the lowest point in that graph as where that error is at a minimum. Optimizers aim to take the model there through successive training runs. In this example, the optimizer that we're using is called ADAM. ADAM is an optimization algorithm that can be used instead of the classical stochastic gradient descent procedure to update network weights iteratively based on the training data. The algorithm is straightforward to implement. And besides being computationally efficient and having little memory requirements, another advantage of ADAM is its invariability due to the diagonal rescaling of the gradients. ADAM is well suited for models that have large data sets, or if you have a lot of parameters that you're adjusting. The method is also very appropriate for problems with very noisy or sparse gradients and non-stationary objectives. In case you're wondering, besides ADAM, some additional optimizers are momentum, which reduces learning rate when the gradient values are small, eta grad, which gives frequently occurring features low learning rates, eta delta improves eta grad by avoiding and reducing LR to 0, and the last one, which is a pretty cool name, FTRL, or follow the regularized leader. I love that name. It works well on wide models. At this time, ADAM and FTRL make really good defaults for deep neural networks, as well as linear models that you're building. Now it's the moment that we've all been waiting for. It's time to train the model that we just defined. We'll train models in Keras by calling the fit method. You can pass parameters to fit that define the number of epochs. Again, an epoch is a complete pass on the entire training data set. Steps per epoch, which is the number of batch iterations before a training epoch is considered finished. Validation data, validation steps, batch size, which determines the number of samples in each mini batch. Its maximum is the number of all samples, and others such as callbacks. Callbacks are utilities called at certain points during model training for activities such as logging and visualization using tools such as TensorBoard. Saving the training iterations to a variable allows for plotting of all your chosen evaluation metrics like mean absolute error, root mean squared error, accuracy, etc., versus the epochs, for example, like you see here. Here's a code snippet with all of the steps put together: the model definition, compilation, fitting, and evaluation. Once trained, the model can now be compilation, fitting, and evaluation. Once trained, the model can now be used for predictions or inferences. You'll need an input function that provides data for the prediction. So back to our example of the housing price model. We could predict the house prices of examples of a 1,500 square foot house and an 1,800 square foot apartment, for example. The predict function in the tf.keras API returns a numpy array or arrays of the predictions. The steps parameter determines the total number of steps before declaring the prediction round finished. Here, since we have just one example, we set steps equal to 1. Setting steps equal to none would also work here. Note, however, that if the input samples in the tf.data dataset or a dataset iterator and steps is set to none, predict will run until the input dataset is exhausted. All right, now it's your turn. In this lab, you'll build a deep neural network model to predict the fair amount using the Keras sequential API. Remember that you have a lab's notebook with partially completed code and that corresponding solution notebook for your reference. Try to do all the to-dos in the student notebook before taking a look at that solution. Have fun. Good luck. All right, now it's your turn. In this lab, you'll build a deep neural network model to predict the fair amount using the Keras sequential API. Remember that you have a lab's notebook with partially completed code and that corresponding solution notebook for your reference. Try to do all the to-dos in the student notebook before taking a look at that solution. Have fun. Good luck.
This short introduction uses Keras, a high-level API to build and train models in TensorFlow. In this lab, you load and prepare the MNIST dataset, convert the samples from integers to floating point numbers, build and train a neural network that classifies images, and then evaluate the accuracy of the model. You will start by building the neural network that classifies images. The next step is to train the neural network that you built, and finally to evaluate the accuracy of the model you achieve. I hope you enjoy it. In the upcoming lab, you will learn how to classify a highly imbalanced dataset in which the number of examples in one class greatly outnumbers the examples in another. You will work with the credit card fraud detection dataset hosted on Kaggle. The aim is to detect a mere 492 fraudulent transactions out of a total of 284,807 transactions. You use Keras to define the model and class weights so that can help the model learn from the imbalanced data. To do that, the first thing is to define and train a model using Keras, including setting class weights. The next step would then be to evaluate the model using various metrics, including precision and recall. You then perform common techniques for dealing with imbalanced data, like class weighting and worker sampling. I hope you have fun.
Now let's talk about deep neural networks with the Keras functional API. In this section, you'll learn how to create wide and deep models in Keras with just a few lines of TensorFlow code. Take a look at this. No, this section is not about ornithology or the study of birds. We all know that seagulls can fly, right? Well, we also know that pigeons can fly as well. It's intuitive that animals with wings can fly, just like we learned growing up. So making that generalization, or that leap, feels kind of natural. Ooh, but what about penguins? Or I guess you could say ostriches for that matter. It's not an easy question to answer, but by jointly training a wide linear model for memorization alongside a deep neural network for generalization, one can combine the strengths of both to bring us one step closer to that human-like intuition. At Google, we call it wide and deep learning. It's useful for generic large-scale regression and classification problems with sparse inputs. And again, that's categorical features with a large number of possible feature values, like high dimensionality. such as recommender systems, search, and ranking problems. Those are some of the most common scenarios. Now, your human brain is a very sophisticated learning machine, formed by rules, by memorizing everyday events, like, hey, that seagull can fly, pigeons can fly, but also generalizing those learnings to things that we haven't seen before. Well, okay, I think animals with wings can fly. Perhaps more powerfully, memorization also allows us to further refine our generalized rules with exceptions, like penguins can't fly. As we're exploring how to advance machine intelligence, we asked ourselves the question, can we teach computers to learn like humans do by combining both the power of memorization with generalization, making that leap from training to inference? This is what a sparse matrix looks like. It's super, super wide with lots and lots of features. You want to use linear models to minimize the number of free parameters. And if the columns are independent, linear models may suffice. Nearby pixels, however, tend to be highly correlated. So putting them through a neural network or a deep neural network, we have the possibility that the inputs get decorrelated and mapped to a lower dimension. Intuitively, this is what happens when your input layer takes each pixel value and the number of hidden nodes. It's much less than the number of input nodes. A wide and deep model architecture is an example of a complex model that can be built rather easily using a Keras functional API. The functional API gives your model the ability to have multiple inputs and outputs. It also allows for models to share layers. And actually, it's a little bit more than that. It allows you to define ad hoc network graphs should you need. With that functional API, models are defined by creating instances of layers and then connecting them directly to each other in pairs, then defining a model that specifies the layers to act as the input and the output to the model, kind of stringing everything together. The functional API, it's a way for you to create models that are more flexible than the sequential API. It can handle models with nonlinear topology, models with shared layers, and models with multiple inputs or outputs. So consider that functional API in those use cases. The API also makes it easy to manipulate multiple inputs and outputs, and this can't be done with a sequential API. Here's a very simple example. Let's say you're building a system for ranking custom issued tickets by priority and then routing them to the right department. Your model could have these 4 inputs. The title of the ticket, that's a text input. The text body of the ticket, also a text input. Any tags added by the user, categorical input. An image representing different logos that could appear on the ticket. It'll then have 2 outputs. A department that should handle the ticket. You could use a classification activation function like softmax, output over the set of departments. And a text sequence with a summary of the text body. In the functional API, models are created by specifying their inputs and outputs in a graph of layers. That means a single graph of layers can be used to generate multiple models. You can treat any model as if it were a layer by calling it on an input or an output of another layer. Let that one sink in, that's kind of cool. Note that by calling a model, you're not just reusing the architecture of the model, you're also reusing its weights. This is an example of what code for an autoencoder might look like. Notice how the operations are treated like functions, with the outputs serving as the inputs in the subsequent layers. Another really good use for the functional API are models that share layers. Shared layers are layer instances that get reused multiple times in the same model. They learn features that correspond to multiple paths in the graph of layers. Shared layers are often used to encode inputs that come from, say, similar places, like 2 different pieces of text that feature relatively the same vocabulary. Since they enable the sharing of the information across these different inputs, and they make it possible to train a model on much less data. If a given word is seen in one of those inputs, that will benefit the processing of all inputs that go in through that shared layer. To share a layer in the functional API, just call the same layer instance multiple times. Okay, now for the fun part. How do you actually create one of these wide and deep models? Okay, so we're going to start by setting up the input layer for the model, using the features of the model data. For this example, we're going to be using the pickup and drop off latitude and longitude, as well as the number of passengers to try to predict the taxi cab fare for a given ride. These inputs will be fed to the wide and deep portions of the model. Using the inputs above, we can then create the deep portion of the model. Layers.dense is a densely connected neural network layer. By stacking multiple layers, we can make it deep. We can also create the wide portion of the model, for example, using dense features, which produces a dense tensor based on a given amount of feature columns that you define. Lastly, how do you bring them both together? We combine the wide and deep portions and compile the model, as you see here. Training, evaluation, and inference work exactly the same way for models built with the sequential API method or the functional API, like you saw with these examples. Okay, so let's talk about some strengths and weaknesses. Strengths. It's less verbose than using Keras.model subclasses. It validates your model while you're defining it. In the functional API, your input specification, that's your shape and your D-type, is created in advance via the input. And every time you call a layer, the layer checks that the specification passed to its matches, its assumptions, and it'll raise a super helpful error message if not. This guarantees that any model that you build with a functional API will run. All debugging, other than conversions-related debugging, will happen statically during the model construction and not at execution time. This is similar to type checking in a compiler. Your functional model is plottable and inspectable. You can plot the model as a graph, and you can easily access intermediate nodes in this graph. For example, to extract and reuse the activations of intermediate layers. Your functional model can be serialized or cloned. Because a functional model is a data structure rather than a piece of code, it's safe to serialize and can be saved as a single file that allows you to recreate the exact same model without having access to any of the original code. See our Saving Serialization guide for more details. I'll provide a link. Here are some weaknesses. It does not support dynamic architectures. The functional API treats models as DAGs, or directed acyclic graphs of those layers. This is true for most deep learning architectures, but not all. For instance, recursive networks, or tree RNNs, do not follow this assumption and cannot be implemented in the functional API. Sometimes you just need to write everything from scratch. When writing advanced architectures, you may want to do things that are outside the scope of defining a DAG of layers. For instance, you may want to expose multiple custom training and inference methods to your model instance. This would require subclassing. Remember, our ultimate goal while model training is to minimize that loss value. It's now time to talk about how you do that at scale with regularization. If you graph the loss curve, both on a training and test dataset, it may look something like this. The graph shows the loss on the y-axis versus the time on the x-axis. Do you notice anything wrong here? Yeah, then loss value is nicely trending down in the training data, but whoa, shoots upward at some point in the test data. That's not good, right? Clearly, there's some amount of memorization or overfitting that's going on here. It seems to be correlated with the number of training iterations. How could we address this? We could reduce the number of training iterations and stop earlier. Early stopping is definitely an option, but there's got to be some more better examples. Well, here's where that regularization keyword comes into the picture. Let's test our intuition using TensorFlow Playground. TensorFlow Playground, if you haven't seen it yet, it's a handy little tool for visualizing how neural networks learn. We use it extensively to intuitively grasp the concepts visually, especially if you're a visual person. Let's draw your attention to the screen. There's something odd going on here. Notice that the region in the bottom left that's looking like blue or bluish, there's nothing in the data suggesting blue. The model's decision boundary is kind of arbitrary or crazy. Why do you think that is? Notice the relative thickness of the 5 lines running from input to output. These lines or edges show the relative weight of those 5 features. The lines emanating from x1 and x2 are much thicker than those coming from the feature crosses. So the feature crosses are contributing far less to the model than the normal or uncrossed features. Removing all the feature crosses gives us a saner model. I'll provide a link for you to try this yourself, and you can see how a curved boundary is suggestive of overfitting that'll disappear, and that test loss will actually converge. After 1,000 iterations, the test loss should be a slightly lower value than when the feature crosses were in play, although your results may vary a bit depending on the dataset. The data in this exercise is basically a linear model plus a little bit of noise. If we use a model that's too complicated, such as the ones with too many of the synthetic features or feature crosses, we give the model an opportunity to squeeze and overfit itself to the training data at the cost of making the model perform badly on test data. Clearly, early stopping can't help us here. It's the model's complexity that we need to bring under control or penalize. But how can we measure model complexity and avoid making it too complex? There's a whole field around this called generalization theory, or G theory, that goes about defining the statistical framework. The easiest way to think about it, though, I love this, is by your own intuition. Based on the 14th century principle laid out by William Occam. Sounds familiar, right? When training a model, we apply Occam's razor, that principle, as our basic heuristic guide in favoring those simpler models, which make less assumptions about your training data. Let's look into some of the most common regularization techniques that help us apply this principle in practice and punish complex models. The idea is to penalize that model complexity. So far in our training process, we've been trying to minimize loss of the data. Given the model, we need to balance that against the complexity of the model. Before we talk too much about how to measure model complexity, let's pause and understand why we said balance complexity against loss. The truth is that oversimplified models are useless. Like taxi cab fare, always gonna be $5, useless. If we take it to the extreme, you could end up with a null model. We need to find the right balance between simplicity and actually accurate fitting of the training data. Later, you'll see that the complexity measure is multiplied by a lambda coefficient, which will allow us to control our emphasis on model simplicity. This makes it yet another hyperparameter that requires your expertise and tuning before the model training starts. It's fun, right? Your optimal lambda value for any given problem is really data dependent, which means that we almost need to spend time tuning this either manually or automated search. I hope that by now this is why this approach is a little bit more principled than just cutting the model off after a certain amount of iterations or early stopping. Regularization is one of those major. Remember, our ultimate goal while model training is to minimize that loss value. It's now time to talk about how you do that at scale with regularization. If you graph the loss curve, both on a training and test data set, it may look something like this. The graph shows the loss on the y-axis versus the time. Regularization is one of those major fields of research within machine learning. There are many published techniques, and I guarantee you, as soon as you watch this, there's many more out there in scientific journals for you to see. We've already mentioned early stopping. There's also dataset augmentations, noise robustness, sparse representations. They're all groups of methods under the umbrella of parameterized norm penalties, and many, many more. In this module, we'll have a closer look at L1 and L2 regularization methods from the parameter norm penalties group of techniques. I like to penalize in the complex models. But before we do that, let's quickly remind ourselves what problem regularization is trying to solve for us. Regularization refers to any technique that helps generalize a model. A generalized model performs well not just on your training data, but also on never before seen test data. Let's take a look at L1 and L2 regularizers. L2 regularization adds a sum of the squared parameter weights term